okay, so this is going to be, categorical semantics, part 2. And so we saw before that in sets, that for definable sets, the symbols and, or, true, false, and then for all and there exist were interpreted using the categorical structure of sets. So our goal now is to kind of replace sets with the general category C with enough structure to interpret our desired fragment of logic. Okay, so so the most basic thing. Okay, so let me go again and kind of remind us how all these fragments of logic break down. So there was these atomic formula, right? And then inside the atomic formula there were Horn formula. Then we had regular, coherent. This split off into intuitionistic and then classical, finite classical first order. This had the geometric, and this was contained in, they both were contained in this infinitary logic. Okay, so we had these different fragments of logic. They were okay. So what we did is we interpreted different formulas. Okay, so like here we had these. We had and true. This and false, and then we added an existential quantifier. We added the for all quantifier way down the line here. Here we added some implication symbol. This is for all and not. Then we had infinite disjunction and infinite conjunction down here. Okay, these were these different fragments of logic, and then we saw that these corresponded to different categorical structures. So in sets, we saw that these operations, these symbols, let's say, corresponded to various operations on subsets. Okay, so maybe I can say them again. So and or true, or let's say I don't know, so various operations, objects, and or true, false, exists, for all, and then let's do not. Okay, so we had all these operations here. So this is for so let's say the power set of some set X. Okay, and this operation here was intersection. this was union. This operation corresponded to the top element. This corresponded to the bottom element. This was a left adjoint. So when we had a morphism from X to Y, we had this inverse image, right? And then this was the projection. So this was a projection, or the image map. This was what was called the dual image, and this was the set theoretic complement. Okay, so the most basic thing. Let me say that. The most basic thing that we need from a category is for the lattice, let's say the poset of subobjects for each object to behave well. In particular, so let's let C be a category. Okay. What we'll need is we need a functor from the opposite category here. So that means it's going to be contravariant to, let's say, category of posets. And what it's going to do is it's going to take some object and it's going to map it to the subobjects of C here. And the most basic thing we want is if we're given a map here, we want to have the pullback map Okay, so this is what we want. Okay, so this is the basic thing. Basic. Okay. If we want more, we can ask for it to have. So we want, products. So when we ask for products, we're gonna get this AND operation. The coproducts. We'll have this, and then we want maximal, minimal subobjects. So, these will correspond to true and false. So these are kind of like initial objects of categories. And okay, we'll just keep on imposing structures. Okay, so for now we'll assume that that our category. So assume our categories enough to interpret let's say Horn formulas. Let's say not Horn coherent. Horn coherent regular. So regular, we add the existential. No, regular, we add the disjunction. So up to regular formulas. So this is called a regular category. And so this has finite limits. Okay, so from now on we'll have this. So the definition, if the pullback functor F star C, let's say C prime to, let's actually do C to C prime. So we're given a map from C to C prime, or C prime to C, sorry, C prime to C, and then this is the opposite thing. Has a left adjoint, has a, and then we'll do it in different things. So left adjoint, let's say right adjoint. So the left adjoint we're going to call like this. So this is from sub. Not A, but I should say has left adjoints. So this thing, then, okay, let's say, then C will be called a hating category. Okay, if it just has this one here, it's called a coherent category. So I guess you get the idea. So depending on how much structure you have, you rename your rename your category. Okay, and the point is hating categories will allow us to interpret all first order formulas. And that there's actually a lemma that says if you have a hating category, right, then it turns out that these sub-object categories have an implication sign that behaves well with respect to the order. So that in particular that the sub-objects are hating algebras. Okay, so we have these categories. So I should mention, I guess, that there's also a notion of a Boolean category. Like this one, I could go on and say more about these, but I guess you can get the idea from what I'm saying already, is that you add structure to the category in order to interpret more formulas. So the Boolean categories are ones where these things are complemented, okay? Meaning that for every object, there exists another object which, when we take the join of them, that we get the maximal element. It turns out that the growth indique topos, so a category equivalent to a category of sheaves on a site, turns out to be a geometric category, okay? And it turns out that geometric categories are hating categories, okay? And Boolean categories are hating categories. So for practical purposes, an ample supply, so a fact, is that a large supply of these categories are provided by categories C, which are equivalent to some category of sheaves on a site. Okay, and these guys are called, i.e., growth indique topos. topuses. Okay, so there are many categories that we can do this with, and I guess the point is that, and maybe people are more familiar with this idea, is that maybe the geometrically minded people is that sheaves always behave. The category of sheaves always behavioral. They have lots of limits, and so when you have when you have all the limits and you have lots of structure to your category, then you're bound to be able to interpret more things. Okay, so we've talked about our categories and what we want from them, and now it's time to do the categorical semantics. So to talk about formulas in context. So the interpretation. So formula in context in our crazy categories C. So, so the idea again, so what's the idea? Is that for terms, we're going to get morphisms. And for formulas, so this is terms, I should say, in context. And for formulas in context, we are going to have subobjects. Now, let's talk about the nature of these things, and let's get to the actual, what we actually need. Okay, so what do we need to fix? So we need to fix sigma and v so that we can talk about our language. And then we also need to fix m, which will be a structure in our crazy category here, where C will be sufficiently rich in terms of what I said previously, and I'll explain what it means for depending on the type of formulas you want to interpret. And so we will, like we did definable sets, we're going to talk about definable objects. So the goal is that given some phi, we're going to have okay, so let me just, we're given some phi and some phi in some context, we're going to have some definable object. Okay, so let's recall that, okay, so let's recall some things about terms, okay? So, okay, so let's recall. Okay. I gotta stick to the order here. Okay, so so terms and expressions for our signature, as we should recall, that have an input and an output, an input sort and an output sort. Okay, the input sort is this, the input sort is what we call the context. Okay, and so in the output sort, so this was just the sort of the term. Okay, so and recall that how we built up all the terms. It was an inductive thing. So we had these basic terms. The basic terms were just plain old variable symbols. And we had the kind of fancy terms. And these were the composition of, let's say, old terms. So in particular, we start with a basic term, and then once we have a term, we're allowed to plug it into this thing with function symbols. Okay, so let me talk about the nature of a term. So of, let's say, the interpretation of a term in a structure. Okay, so let's talk about this. So here we have this dude here. Okay, so this part here is the structure. Here we had variables, so x1 maybe to xn variables, and we had that xi was of sort ai. So this is the sort notation. This doesn't necessarily mean it's exactly an element of. And then here, this t, it has an output sort c. Okay, so this is all inside. So maybe I can do this, put it in parentheses. So this is a term, okay? And so what we end up getting is, okay, so this is all the pieces. And what we have is that t x of m, okay, well, we have these xi's. They have all sorts ai's. So we'll get something from a1 cross so on to an. So this, the interpretation of this in the structure to the interpretation of this guy. So now this is a morphism in the category. So this is a morphism in our category C. Okay, how do we construct these guys? So the construction of these dudes. There's so again. This is for a fixed. We need a fixed context. So x. Okay, and okay, and so the base case. Okay, was when we had these basic terms. So here we have that the term is just a single variable symbol. Okay, and so in this case, the output of this term will be AI. Okay, and in this case, what do? We define the interpretation of this term to the m. So this is going to be pi I, right, which is just this projection to AI. Okay, but now it's interpreted here like so. So this is the ith coordinate. The inductive step okay, so for the inductive step, t of x, okay, so here, we'll, like I said, we'll have t of x. This is our term here, and it's a composition of a bunch of different terms. Okay, and then it needs to be compatible because this is how we defined our terms. So, so here ti. So this all needs to make sense. So what does that mean? So that means ti of x of type. Let's say the sort is bi. Let's do the sort. Okay, so that's what sort says, and then f. And then we're going to use the notation that we had for function symbols. Okay, it needs to be of the appropriate thing. Okay, and so okay, so now to interpret this, we okay, we have a symbol here for f, right? So okay, in the interpretation, remember what we had for a model. So note that fm is given. And then say if these were variable symbols, these were also given. Okay, so the very, very basic inductive step is you take some function and you plug these in. Okay, but now here this could be, you know, composition, like multiple ways down we have this composition. Okay, so now we have here by induction. So this guy is a function from, so what does it take in? It takes in a to the m. A is this big tuple, and it goes to bi to the m. Okay, so this is also given. And now tx to the m is the composition so here A, okay, and it goes to B, so to the M. So this thing is BI or B1 cross BN or M. Let's see, M. These shouldn't be the same. Okay, N and M should not be the same because in general they're not. Okay, so here to BM. Okay, and then this guy is a function symbol. These are given, Cm. So the function is of this type here, and we can interpret it. Okay, so this one is just the product of the TIs. Okay, I'll do that for the notation there. Okay, and so this is i.e. So T. So this is equal to Fm composed with Ti to the m. Okay, so this is how we build up these functions. So to repeat, so given these terms, we can talk about what functions they're going to give us, or what morphisms in the category. So literally, they're going to be morphisms in the category. So this is a morphism in C. Okay, now that we've talked about terms in context, we can talk about how to build up the formula in context. So how did I do this heading? Okay, so this explains how to do this. I didn't give a heading. So now, so for formula in context, now we will show how to interpret formula in context in M. Okay, so this is going to be an inductive thing again. So let me just remark about the nature of this. So the nature of these. So we're going to give in phi of x. So this is going to be here. So this is a formula in context. Let's say x is x1 to xn, where the sort of xi will be ai. So this will be the sort again. And so what are we actually going to do? So this guy here, so this is our structure again. So this guy here is going to be so this is going to be a sub-object of a to the m. So this thing's a here. Okay, so this will be a subobject of a to the m. So i.e., maybe I can put parentheses around this, i.e., this dude is an element of sub c of a to the m. Okay, and I want to talk about how we build these up. Okay, so this is what we're going for. Let me say this before we even start. Once we have these, so this is so let me give a definition. Okay, I mean I'm gonna give a terminology. This is more terminology because I haven't really defined it, but I'll define these in a second. The phi xm are called definable objects. And the collection of them will be denoted by DFBLM. Okay, so M is again a structure with values in a category. So so like definable sets, these are going to be definable objects. So I'm going to omit the brackets there. Okay, so I may omit them. Okay, so before going about talking about what these things are, so what does this do for us? So again, this will allow us to extract truth values for deductive statements. Okay, so let's remember that, let's do this. Okay, so then let's give a definition. This thing here, okay, so what do we have? We have our formula that says something like, we have two formulas in context X, and we want to know whether or not it's true in M. Okay, so supposing the category is rich enough and that both of these formulas here make sense, this thing is going to be either true or false. Depending on whether or not, well, I guess it could be true or false or what, but we've cooked it up so that our categories are going to be Hayden categories. So depending on whether this thing is less than or equal to M in, so let's say the context given, let's say phi of x, psi of x, in context x is equal to x1 to xn, oh man, I ran out of space. Let's say with xi and ai, so this is the sort again. This thing is going to be true depending on whether or not this formula holds in this dude here. Sub c of, and then we have a to the m, where a is this big product here. Okay, so this is the big thing here. Okay, so this formula here is equal to this thing here. Okay, so we have this proposition here, and then we have this dude here. And so this guy, whether or not it's true or false, depends on the order of this guy in this thing here, which is if C is a hating category, then this is a hating algebra. So if this is a, yeah, hopefully I didn't block the microphone there. We'll see. Okay, so this is the punchline. So what am I doing? I said, what's the nature of these definable objects? They're sub-objects of this thing, blah, 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 blah. Why do we care? We care because it allows us to do this ordering on these sub-objects. Okay, if we're given formula in this context, we can see whether one applies the other by looking at the order in this hating algebra. That being said, now we're motivated to define these things. So, okay, so the actual definition. So the definition, how we construct. Okay, so this is the kind of the cool part of this whole thing. So we talked about our terms and their morphisms, and we have these basic objects. So so first let's talk about atomic formula. So atomic. So remember that. So if phi is atomic, then it has the okay. So like we could take a relation here. So this is an atomic formula in context. Again, x is x1 to xn. Xi's are in AI. And this A is this big product of all these AIs. That's the notation for this. These are really about sorts, okay? And so the relation here, so this is the atomic thing. In the interpretation, we have a freebie. So remember that R x of m was given. So this was given in the definition of the structure. Of a structure. Okay, so we already have these sub-objects here. Okay, but how do we do it for terms? Okay, so atomic formulas have terms involved in them. Okay, so this thing here is terms. So what do we need to kind of specify? Let's say that Ti is of terms Bi. Okay, so then here we need to. It's essentially done by base change here. So we have our sub-object here to. So this is given in A to the m, and then our term. Oh, sorry. This goes from B to the m in this particular example because here R reads in B's. Okay, and then so B is the products of these Bi's. Okay, or Bj's, I guess. This should be an m, I guess. So this is m. So because they're different. Okay, so now the term here, as we said, was a function or a morphism in this category, which takes things from A's and it goes into these B guys. So AM. Okay, and then the idea is that this general relation here are composed with T of X. So this is defined via the fiber product. Okay, lastly, for out of the atomic things, we had equality. Okay, so we had two terms. So if we're given s and t, so we could have let's say t of x is equal to s of x. Let's say they're both of sort t s of sort b. Then okay, so these two things were functions from the a's to b's. So we had a, which was this big product, and we had this b here. So we have two functions here, s, t, and then we had b's here. And so when we interpret s and t, we get two guys here. And to make them equality, we can just talk about the equalizer of t of m and s of m. And this sub-object here, this is defined to be, this is by definition, equal to t, I'm going to omit the s's for notation purposes. So this is defined, this is defined to be the equalizer of these two morphisms here. So again, this goes to the richness of the category that we want, and it's saying that our category, in order to make sense of equality, needs to have equalizers. Okay, so now we can go on and talk about how to build the other formulas from this. Okay, so these are our atomic formulas, and so far we just need equalizers in products. So we need limits. So okay, so Horn formulas. So what kind of things did we add for the Horn formulas? So we had finite conjunction of two formulas. Or sorry, we had finite conjunctions, which is sufficient to do conjunction of two formulas. So to do that, okay, well, we start with our atomic formula. So now we're going to do the inductive step. So let's say that they have context. So they have the same context A. So here we have our interpretation of psi, and then we have the interpretation of x, and we have these two sub-objects here. And now they're from our, so we have this guy here, and so we have the meat of these two guys. So here, cross psi x to the m. So this is, by definition, this is the definition of the fiber product of two, or the intersection of two guys. So this is defined to be phi and psi of m is defined to be this intersection. So this uses products. So fiber products. Or you could say it in another way. It says that sub c of am needs to have this meet operation. Okay, so I should say that here, you know, the one for disjunction is true, but let me just say this. Okay, so let's start with true since we're sticking with Horn formulas. So for true, this is using that we have a terminal object in this sub c of am. Okay, that's cool. And I think this comes from I think like something like sub-object classifiers and maybe the terminal object of a category. Okay, maybe someone can say this. I need to check that. So now we have Horn formulas. These are contained in, so now to add the regular things, we have this disjunction. Okay, and then we have this guy here, the false symbol. And then for hating, okay, so I guess then we could do hating or coherent, but let's talk about the hating implication. So this uses a hating implication on this guy, sub C of AM. Okay, here, so this uses coproducts. So this is very similar to, these two are very similar. This uses coproducts, or meets, or sorry, joins. So it uses the fact that the sub-object lattice has a lattice, and this is uses initial objects. Okay, more interestingly, we get to coherent and classical logic. Okay, so again, notice again that this is all built up inductively. Okay, these parts are all built up inductively from the atomic formula, which were given as part of the structure. Okay, so for quantifiers, so let's say there exists a y psi of xy. So something like this formula here. So how do we interpret this? So this is going to be defined to be equal to, so here, so x is of sort A. Let's say y has a new sort. So y is sort B. Okay. So here, we know that we have this guy, and this guy is contained in AM cross BM. And we know that we have this projection away from this pi of A M, okay? And this goes to just here, okay? And we saw previously that that the existential quantifier was about this projection map, and so this was the image here. So this is the image of the map. But here, what we're going to define. So let me hold on a second. Okay, I fixed things up, and we saw that this guy here, there was this adjoint here for the pullback map. So this adjoint here, AM, and we saw that for sets it worked well, so we'll just define it like this for in general. So we take this guy, and then we do this, and this will be in sub C of AM. Okay, and so the for all quantifier, when we want to interpret this is done similarly. But using the right adjoint. For the pullback map, pi A sub M, instead of the other one, instead of the left adjoint. Okay, so i.e. the, oh, sorry. So let me say this again. So by definition, what did we do here? This is the definition of, so there exists a y psi xy M. Okay, so this is the definition. The definition of the interpretation here is this sub-object here. Okay. So we do similarly for this. So, so what's this saying? This is saying for all y psi of xy, this thing M, is defined to be equal to this for all pi a m here of this dude, the guy that we by inductive hypothesis we can assume exists. All right, so for the infinitary logic, it's a pretty similar story. Okay, so this is awesome. This is great. Now we're kind of worried now. Maybe this doesn't make sense. So like, we should check that this makes sense in some sort of example, huh? So here we'll take C to be the category of sets, and then we'll just look at a bounded formula. Okay, so we should be able to make a truth value. So okay, so let's take phi of y to be in our language. So signature doesn't matter at all, and then we'll take y to be b. So this is going to be just in the sort terminology, and then we can create a bounded formula out of this. So psi, this is going to be the bounded formula for all y phi of y. Okay, so this is again in this thing, but now this is bounded. So this is this has an empty sort. Okay, no free variables. F v psi is empty. Okay, so this is cool. Okay, so now so let's look at what this means. So for all y phi of y to the m. Okay, so there's a couple ways to do this. So first we should observe that this thing here is in, so we should take the sort of this thing, psi, to the m, so we interpret it as an object. Well, this thing here is the trivial sort. So this is the empty sort. To the m, which is our terminal object, which is just a point. Okay, so this was part of the structure, the idea of the structure, because we had a terminal object in our Levere category. Okay, and so that being said, let's notice now that the power set of the point here is really the empty set and the point itself. So this thing here corresponds to true and this one corresponds to false. So this says that there will be a truth value that returns true or false as expected. Whew. Okay, so this is nice because it has a terminal object here. On the other hand, we can look at this in a different way. So remember that we had, so what did we do? So so we had B, and then I guess we could cross it with a point here, and we project down to a point. Okay, so we can really put M's here. So this is really the identity under concatenation. So maybe I shouldn't have written it like this. So this is the identity under concatenation. Okay, so remember that in our Levere category, when we constructed our Levere category, we just had a bunch of strings, okay? And so here, this is the projection of B. Okay, and then and actually we're defining it in terms of the truth value actually in terms of the adjoint functor, because our definition called for the following. It said that for all y, let's say phi of y, m. Okay, this was defined to be equal to. So now we use the fact that there's this adjoint here, pi m. Pi of b to the m, of now we apply this to this subobject. And the subobject is, I mean, we could also do it for the exist thing, okay? We'll do it for the exist thing in a second. So this phi y of n, so we had this definable set here. And this thing, as we saw before, for categories, so this is pi bm, for the category of sets, so this is the co-image of m. Or sorry, the dual image. Dual image. Okay, similarly here, if we were going to do this formula here, this bounded formula, so this guy is that there exists some pi of bm here. So this is this functor applied to, and we're working in sets, this definable subset here, and this is just the image of pi of bm of okay, so yeah, and so what this is really, so this is okay, so what we're really determining is whether or not this thing is empty or not. Okay, so this is really, I mean, in normal terminology, if we're not viewing it as a subobject or as a power set element, this is just pi of bm of this definable set here, m. Okay, so this is really just detecting whether or not it's empty. So if this is empty, the image is going to be non-zero, and then according to how the truth tables shake down, this says whether or not it's true or false. Okay, so this is how you interpret things. That's all I have to say about this. So thanks for watching. So I forgot to do one of the kind of the fun parts. The fruits of the labor is defining models of theories. So so let's take a definition. So we will say that, let's fix everything. Sigma be a signature. Let M be a sigma structure in some category C. Okay, and then we'll say that, so suppose phi psi and phi in L sigma have a shared context X with sort A. Okay, and then this could be a tuple, and this could be a tuple here. Then we'll say that at M M models the deduction phi implies psi and right. So M models this deduction if and only if, and we defined this before, so that this thing, psi m, and so this is true. Okay, so I mean I guess I don't need to write that, but and remember that this is this thing means this formula here means that psi of x is less than or equal to of m. So this is this object, and we have phi of x of m in the sub-objects here of this category where we take a to the m. Okay, so this is the sort of the x variables. So M models this formula. So this formula or this thing will be true if we have this containment here. Okay, and so also for this definition, we need C to have enough structure to be able to interpret / define the formula. Okay, so that's kind of warning here. So this is what we need. Okay, so this is what it means to be model a formula. Definition. So let T a subset of the set of all deductions. So everything like this. Let's say psi. Let's do it this way this time. So these are all these things. So we take some theory and some signature with some variables. Okay, so we have this language, and we have the subset. So we see that M. Okay, so we also need to take, let me just define everything. M is going to be a structure for this category. And again, we suppose all formula are interpretable in the category C. Okay, so we have this theory, we have our structure, we said that our formulas are interpretable, and now we can make the definition that M is a model of T, and then this thing is and then this is the same thing as writing this symbol. So this is writing if and only if M proves, and then we have some formula P. So this is maybe this one of these deductions for all P and T. Okay, so this is what it means to be modeled. Model, okay? And so that's cool. So now we can define the category. So definition. So model T of C this is the category of models. Of T valued in the category. And so this is just this is the subcategory of structures which are just models in T. So this is the subcategory. Okay, so this is the category of models valued in T. So this is how we define a model of a theory with values in a category. So this kind of gets interesting because if you take the theory of groups and you take C to be topological spaces, then the models that you get are topological groups. So this is the kind of thing that happens. And then you can kind of go blue in the face with that idea. So there's kind of an interesting fact, and what now I'm driving at is a different type of morphism for models. So, but let me just first give you a fact: is that if phi, let's do something. So let phi of x be a formula in context for x. Xn, and let's say that the sort of x is A, and this is really a product of AI, it's a bunch of other sorts. Okay, and then, so we have this formula in context here. If phi is geometric, so is geometric, and let's say h from m to n is a morphism in the category of structures with values in C, then we have the following commutative diagram. So there exists a diagram like this. So we can interpret this in M. It's a subobject of A to the M. Okay. Then there's this H of A. So this is the functor that's induced by the morphism of structures here to N. And we have this phi of X to the N. Okay. Okay, this is important. This is crucial. This is not true. This is not true if the formula is not geometric. And remember, geometric, for example, you're not allowed to, in general, okay, so this has for all quantifiers. Okay, so this is kind of interesting. So I mean, you're not allowed to have for all quantifiers, right? So you can have infinite disjunction, excuse me, you can have infinite disjunction, but you can't have for all quantifiers. Yeah, so, okay, so let me just say what the proof idea is. The proof idea, and most of them are, and then I'll put a reference in the bottom. The proof idea is that is induction on how you build formula. On how the formulas are built. Plus, the properties of C. So I guess C needs to be a geometric category in order to interpret a geometric formula. Okay. Okay. That being said, because these don't always commute, we're going to create a new type of morphism between models. Okay. So definition. So let M and N an element of be models for a theory with values in a category. And then we're going to take a morphism of these things, be a morphism. So this is just a morphism of structures. We say that F is elementary provided the diagram, so provided for every first order formula, every first order formula. Okay, I'm not defining every, of course, but I'm just saying that's emphasis on every. For every first order formula phi of x in context x with sort A, the diagram, the induced diagram, and then I'm going to write down the diagram. This thing M, A of M, A of N, so this whole thing commutes. Let's see. Let me just write it in the diagram. Blah, comma, commutes. Okay, and so this is what an elementary morphism is for models, and so, or maybe I should have called this model, not models, but okay, you guys know what I meant. And so definition. So this is maybe a notation. Model, and then we're going to put a subscript E here of T with values in C. So this is going to be okay, so this is going to be the category of T models in C with elementary morphisms, elementary embeddings as morphisms. So this is an important thing. This is really confusing to me, actually, the first time so I guess it's because of this fact here that this thing doesn't really hold, why we're actually working with elementary embeddings instead of all random, morphisms with structures off the street. Yeah, and so this is why the model theorists use this. Okay, so that's all I wanted to say about this.